earlier we have seen the derivation process. So we assume the linear model and we try to come up with the mean squared error, and then we take the partial derivative of the mean squared error. Take a look at the same formula from the probabilistic perspective. So linear regression can be talked as where we want to find out a Gaussian distribution that is represented by where mean is equivalent to W transpose X, and the variance is sigma square. Well, if you have this assumption, then we can easily come up with the log likelihood. So log likelihood is multiplication of likelihood, but multiplication of those probabilities is so small, so we put log in front of it. So, well, imagine the Gaussian distribution parameterized by Wx and sigma, where you can come up with the probabilistic notation for each instance as this. And we take the log of it and we take the summation. And if you address this, the left-hand side, where you can come up with this. So out of this right-hand side, where you can find out the form of mean square error again. And here, the prediction side, again, this is W transpose X. So if you put in this W transpose X, where the process of optimizing this log likelihood is equivalent to optimizing W in this form. And well, since the form is the same as what we was working with, so eventually, if you take the partial derivative and well, try to set it to 0, and you can come up with the same analytical solution from here. So we have talked about two things. So one is we're trying to define the mean squared error from the matrix multiplication and try to optimize that term. Well, that is equivalent to probabilistic point of view. So you can imagine you're going to model a Gaussian distribution parameterized by W transpose X, and the variance is sigma square. And eventually you will have this notation for log likelihood. And if you try to optimize it in terms of W, where the rest of the process is equivalent to optimizing the previous slide. So eventually you can have the same analytical solution. So, well, we got stuck at here. So, well, this is from here, you can imagine W is X transpose X inverse X transpose Y. But, well, we know that, well, this is only possible when X transpose X is invertible. And that is often not the case. So we want to find out some alternative way to address this. So what we have discussed is described in more theoretical level. So where X should be full length, and the proof is given here. And we are going to move on to the alternative solution. So alternative solution is a famous gradient descent algorithm.